Okay, so we're carrying on trying to understand the Mitchell-Benabou language rules. I just want to say regarding the last little video snippet, I think I meant to say that G is an arrow from A to B. I thought that was clear anyway from the algebra, but I may have said it differently. Anyway, so now we've got some understanding of what this kind of set builder notation is meaning. It's basically just abbreviation for this lambda notation. But there's another important piece of notation which we want to understand, which is what does this for all mean? And the short answer is that for all capital A means the classifying arrow of the name of TA, where TA is true after exclamation mark A. And so really the name of TA is TA after P2 all transposed. Okay, and then that's a sub-object of omega to the power of A, and it has a classifying arrow which we call for all A. Now, what does it mean then to write for all A after one of these sets after one of these set notation things? And the short answer is that it means that this set is the full sub-object. I mean, it basically means we have the full sub-object here. So, in other words, the sub-object, when well, no, that's not what it means. Basically, what this is saying is that we're then talking when we say for all A, and then this set of A dash such that GA dash equals B. What we're really saying here is this is going to be a classifying arrow, and it's going to be classifying the collection of all B, which make this condition hold for all A. Okay, so that's what it's saying, right? So we can understand this. So firstly, here's a little bit of notation then. What's it mean when we say this is a term, okay? Let's say it's a term of type omega, it's a formula. So what's it mean when we say for all A dash in A, we have phi? Well, that's just an abbreviation for saying for all A, we have this set builder notation, collection of A dash in A such that phi. And the way we can really read this is that this kind of set thing, the set of all A dash such that phi, is actually all of A. That's what this is really a claim of. But, we can actually understand what this means more concretely. If we get rid of a set builder notation, go back to lambda notation, so we have for all A, lambda A dash of phi, and also replace this for all A with what it really is, which is the classifying arrow of the name of true A. So for classifying arrow name of true A of lambda A dash of phi. That's what this really means, okay? There's lots of kind of abbreviations and stuff going on here. But how do we understand what it means? Well, basically, like I say, what it means is it's classifying the sub-object of B, which makes this condition phi hold for all A. But let's see this. Okay, so let's consider a general element, a H element beta of B. Well, beta is going to be in this extension here of B such that for all A dash, we have GA dash equals B, if and only if, just expanding it out, we have for all A, interpretation of the set of A dash such that GA dash equals B on beta is true. Now, we use the fact that for all A's is classifying arrow, which we understand. So it means that interpretation of the set of A dash such that GA dash equals B on beta is in transpose of TA P2, well, we can rewrite as that saying it's equal to transpose of TA P2 after exclamation mark H. Now, we know what this set builder notation means. It's just an abbreviation for this lambda notation, and we evaluated it already to be transpose of delta B after P1 comma GP2 after beta, and then we've got that's equal to this transpose here. If we transpose both sides, we get that delta B of P1 comma GP2 of beta times 1A equals true after exclamation mark H times A. And we can clean that up to basically say that beta P1 dash equals GP2 dash. Now it's easier to understand what this means when we consider a special case where H is a terminal object, in which case, as I've proved in green here, this is equivalent to saying that G is equal to beta after exclamation mark A. So in other words, G is always beta, which if you think about it, makes sense, right? Because beta is such that GA dash is equal to beta for all A dash. So in other words, G is constantly beta, okay? So that makes sense. Now, I want to connect this with another occurrence of this for all notation in a slightly different looking format, but actually it's pretty much exactly the same thing when we understand. So let's write chi of R to be the interpretation of GA equals B. I'm not going to worry too much about whether I'm using A or A dash for the moment, because I'm connecting with something that doesn't involve terms and interpretations and stuff, but it's not too relevant anyway. So the point is that what this is then saying, what this sort of conclusion of our result would be saying then is that beta times 1A is in R. Okay, that's equivalent to saying that chi of R after beta times 1A is true, which is what I've got up here, okay? And we've just shown that that happens if and only if beta is in this extension here of for all A, GA equals B. Now let's see that occur in a different way. So previously, in the last chapter, which I have gone through in the topos videos, we introduced this notation that for a relation which is a relation. I think it's a monic from B times. It's a monic R into B times A general one. We have that for one of these generalized elements, like what I've got here, we have that beta times 1A is in R if and only if beta is in for all AR, where for all AR is a sub-object classified by for all A after transpose of chi R. But doesn't this look pretty much the same? Well, we've got this beta in for all AR, it's pretty much the same as saying beta is in this sub-object here, which is classified by for all A dash GA dash equals B. So you see that these notations are very similar, and moreover, well, I should say, this is the classifying arrow of R, really. Kind of like it. I mean, it's a term, so we can't really compare apples and oranges like that, but let's just see this more clearly. So what we're basically saying is that, I mean, obviously, if we call right, if we say that we're going to have, I'm just talking roughly here, but if we say we're going to have B comma A in this relation R, if GA equals B, then we're going to have that chi R is basically going to be this interpretation of GA equals B, right? And then this kind of set builder notation is just going to be the transpose of chi R. And so if we pull back true along for all A after chi R, we basically get a sub-object like this, which in the previous chapter was called for all AR. But now we're calling it this extension thing, the extension that the collection of B, such that for all A dash, GA dash equals B. Okay, so we see that they're basically pretty much the same thing. And thus we have the similar notation. It's all matching up pretty nicely. And I mean, basically what I've been showing here is the kind of meaningfulness of this type of notation here in something satisfying these relations. And it particularly works when we consider a global element beta of this extension here, because then we really get something which exactly satisfies this. But more generally, we have these kind of projections entering the story.